We are now moving on to another interesting phase of the two-day conference. This is another keynote address. The subject is collaboration as a way forward for semiconductor technology. And I would request Dr. Gary Patton to kindly come over for the keynote address. He's the Vice President, IBM Semiconductor Research and Development Center, has held several management and executive positions in IBM before reaching this position. So ladies and gentlemen, put your hands together and let's welcome Dr. Gary Patton. It's all yours, sir.
Thank you. I am truly very excited to be here. I love the energy here in India. I think most people recognize IBM has a very large presence, very large investment. And I'm very proud of the fact that a little over 5 years ago, I launched our Semiconductor Research and Development Center here in Bangalore. And that has grown to be a very large portion of my organization and a very critical part of our activities to deliver leadership technology to both IBM and to our partners. I'm going to talk today about how to build a collaborative ecosystem. I think that's very important for really being able to deliver leading-edge products that have the differentiation from a cost perspective, from a performance perspective, and from a power perspective. I think it's been truly an exciting time in our industry here over the last decade, but it's worth noting this has not been a phenomenon of the last decade. It's been a journey, and I think that's highlighted very well in this chart, which shows the cost of what $1,000 would buy you in terms of computing over the last century. And you can see it's been a steady progression. Basically, this has improved 15 orders of magnitude over the last century. And it has been accelerating. In just the last 30 years, it's gone up by 6 orders of magnitude, which may be why we feel this rate and pace is, we're on a treadmill, as was shown at the beginning. This is accelerating. But it really started back at the beginning of the century with the mechanical era, then electrical mechanical, vacuum tubes, discrete transistors, and then, of course, integrated circuits. And then next is nanotechnology, and that's a big focus for us in our research division, plotting out the future. And these innovations that will lay the groundwork for the next technologies literally take over 10 years in the research phase before they're ready for development. Just to highlight a couple examples, if we go back to the early 1960s, IBM came out with the System 360. That was a huge breakthrough in server, in computing, and really defined the industry in that time period. But what was in that, at the heart of that, was a module that had 6 transistors and 4 resistors. 6 transistors, so 10 devices. If you think about it today, our Watson system, which is now being used in the financial and healthcare industry to solve really tough problems, is powered by 360 Power 7 chips, 360. And each one of those has 1.2 billion transistors. Tremendous amount of integration on it. Compare that to the example I just showed you a moment ago from 50 years ago. What a change. Now this advancement is not just in the high-end computing, of course, as we all know. It's resulted in a huge explosion in consumer devices, as you can see here, from smartphones to games to digital TV. And of course, behind it is the network and the things like the IBM servers support. And it's really resulted in an explosion. I'm not going to go through every one of these examples, but today there's literally 1 trillion devices that are connected in some way to the internet, which has resulted in the ability to do an incredible amount of computing on your phone, do smart cities, smart transportation, smart power. And the amount of data has basically doubled in just the last 3 years to now 225,000 terabytes per month, which is an incredible amount of global traffic. And India represents a huge opportunity as well as a leader in this area of leveraging the mobile computing. India is the second largest market with 865 million wireless subscribers. That's basically roughly 3 out of 4 people. And a real tremendous opportunity because it's a much smaller percent that is actually using smartphones. And as smartphones become more affordable, we can expect that that will grow over the next decade. And I mentioned India's been a pioneer. India's been a pioneer in using mobile communications in the banking, recognizing, given the wide array of villages and cities in India, it would be very difficult to make banking close for everyone. So you pioneered the use of mobile computing and mobile connections for being able to do banking. The other key area is in the area of farming. That's been a huge explosion. Just in the last couple of years, it's grown from 3 million farmers to 10 million that are using the internet and mobile computing to be able to find out about prices, crop volumes, weather forecasting, to be able to do better farming. And it's estimated that the value of that in terms of improvement in farming is roughly $10 billion. And this just shows a cute example of somebody on a farm using mobile computing to do their activities. So what's driven this explosion? At the end of the day, it's all about economics. If you can make smaller features, you get better performance, you get better cost per function, you can do more applications. You know, what you can do on a phone has grown tremendously in just the last few years. And guess what? An explosion in the marketplace. And it's highlighted really on these two graphs. On the lower left is the relative price of a transistor, which has gone down by about 5 orders of magnitude over the last roughly 30 years. And on the right is the consumption of transistors, so the number of transistors consumed per year. And that's gone up actually by over 6 orders of magnitude in that same time period. So all of that drives this economics. Now, if you go back to my earlier chart and I showed this exponential growth in the ability to compute, and it kind of looks like this nice linear function. The reality is it goes in step functions. We have an innovation. We're usually able to leverage it for about a decade, and then the benefits start to slow down, and we have to come up with some new innovations. If I look back in the 1990s, we had simple CMOS technology. You scale the horizontal dimensions, the vertical dimensions, the power supply voltage, and you got better density, better cost, better performance, and power density stayed constant. And that fueled the laptop era, that fueled the whole wired infrastructure era, so basically the era of portable computing. But around 2000, we got to the gate oxide limit. The gate oxide got to be about 3 atomic layers, and we couldn't scale it anymore. We could have said at that point, it's game over, but we didn't. We innovated. We said, hey, and this is pretty revolutionary, let's change the fundamental properties of silicon. I think that's a pretty bold idea. And that's what we did. We said, if we can introduce strain into the silicon, we can actually enhance the mobility and speed up the devices. And so things like embedded tensile and compressive nitride liners were introduced. And then more recently, high-k metal gate. Let's change the electrical properties of the gate oxide. In the case of IBM, we introduced high-performance embedded DRAM. We recognized the ability to get data in and out of our cores, our microprocessor cores, was a key limiter. And to be able to put very low power, very dense memory onto the chip along with the cores would result in a huge performance improvement. For us, it was worth almost a full technology node in power, in performance, and in density. Anyway, this era basically resulted in the explosion in personal computing and has led us to the smartphone era. Now, we're at another one of these transition points right now. We've reached really the limit of being able to play this game of engineering the material and putting strain or high-k metal gate. We really need to do something different. And this is the end of what I call the planar device era. Now we're in what we're calling the 3D era. And that's 3D devices, known as FinFETs, and 3D integration. This is the stacking of chips. And this is going to result in a real explosion over the next decade in the mobile interconnect of devices. That should take us well into the 2020 time period, but at some point, 3D will run its course, and we'll hit the atomic dimension limit, and we have to come up with something different. It won't be game over. We're going to go to new types of materials, and this is where we come into the nanotechnology era. So things like carbon nanotubes, silicon nanowires, 3-5 devices. The use of photonics, light, rather than electrical signals, would have tremendous benefit in improving the speed of the circuits. And that's going to result in a whole new era of what I would call wearable devices, basically computing pretty much everywhere and with you all the time. Now, I talked a lot in that last chart about devices and atoms and molecules, but at the end of the day, it's not about atoms and molecules. It's about products. That's what we're focused on. That's what we're driving for, products that have better differentiation, better cost, better power, better performance. But to get there really requires optimization of the entire stack because of the complexity of the products and the complexity of the technology. It means optimizing the technology, the chip design, and the products to get that differentiated value. And you hear now in the industry a lot of fabless companies talking about becoming virtual IDMs, so virtual fully integrated companies, by partnering with their foundry partners. We recognize the advantage of this. We are an IDM in IBM, and that's how we do business. And that's how we generated the Watson system, for example. We optimized the technology and the chip design and the system all together to generate that system. And I highlighted the example of the chip. Power 7 Plus is what's behind it. Close to 600 square millimeter chip. It's huge. And with basically over 1 billion transistors.